All right, so continuing from the last video, we're going to continue looking at permutations and combinations. If you haven't watched the last videos, you need to watch these in order because there's a lot of continuation. You're going to be lost. Make sure you watch them in order. So we're going to look at some more permutation stuff and permutations with some different things that are going to go on, some different things that could change up how those permutations go. So let's start with a problem. And like magic, there's our problem. 8 students run a race. How many different ways could the students finish first, second, and third? So we're still going to use the counting principle here, but this is going to help develop another formula with permutations. So when we look at first place, there are 8 students running that race. Assuming that they all have the chance to finish first, that means 8 possible students could finish in first place. A student finishes first, then whoever comes in second, that only leaves 7 students left to come in second place. And so, just like we did with the counting principle in the last video, we're going to multiply by 7. And then finally, for third place, we already have a student that finished first, and we already have a student that finished second, so that means that there are only 6 students left that could finish in third place. If we multiply all of those together, we get 336. There are 336 different ways that these 8 students could finish first, second, and third. That doesn't take into account 4th, 5th, 6th, anything beyond that, right? After the third place has finished, it doesn't matter the remaining 5 positions according to this problem. So we're only looking at positions 1, 2, and 3. So it's not just 8 factorial. However, we do have a formula that would allow us to come up with this instead of working it through this way. So we set it up in this fashion. This is on, I'm going to write this down for you, this is on page 620 in your book. And so if you go to your book, page 620, you will see this definition of permutations of n elements taken r at a time. And so the way that we set this up, we're doing a permutation, so we use the capital letter P, and then we do 2 different subscripts. We do a subscript, I don't know why that just happened, let me get rid of that. Oh, let me put that back in there, there we go. We do a subscript to the left, that is n, and then we do a subscript to the right, that is r. And so the way that this is read is we're doing a permutation of n things taken r. Right? We could also read it as n choose r is another way that we'll say that. The formula for that is a very, very brief, quick, and easy formula. We simply do n factorial, that was discussed in our last video, and we divide it by n minus r factorial. So in this specific problem, we are looking at taking 8 different runners, so that's the total amount, and we're going to choose 3 of them. We have to be very, very careful that we don't flip those around. You can't have 3 things chosen 8 different ways, but you can have 8 things chosen 3 different ways, right? So the r number should always be less than n. And so if we plug that into our formula, we have 8 factorial divided by the quantity 8 minus 3 factorial. And so if we clean that up a little bit, we have still 8 factorial in the numerator, and in the denominator, 8 minus 3 is 5, and so in the denominator we have 5 factorial. So if you remember what factorials mean, they just mean you start with that number and multiply every integer below it down to 1. And so in the numerator, this means 8 times 7 times 6 times 5 times 4 times 3 times 2 times 1. In the denominator, we have 5 factorial. Well, that means 5 times 4 times 3 times 2 times 1. Take a look at what happens. 1's cancel, 2's, 3's reduce, 4's reduce, 5's reduce, and OMG, we're left with 8 times 7 times 6, which is 336, exactly what we got up here when we did the problem just by looking at the counting principle. OMG, right? So you can use the counting principle for that, but you can also utilize this permutation formula. That permutation formula will allow you to choose as many different things as many different ways as possible. If you recall yesterday, we had a problem. I don't know why that line got there. If you recall yesterday, we had a problem that talked about Gotham City license plates. We had 3 letters, and then we had 4 numbers, and we gave a problem where the letters could be anything, and then we gave the problem where the letters couldn't repeat. If you recall, we ended up with an answer of 78,624,000 different license plates that could be created. We could do the same thing with the permutation rule that we just have here instead of doing the counting principle. That would look something like this. If you recall, the first 3 entries in that license plate were 3 different letters. So what we could have done is we could have just looked at the permutation of 26 letters where we're choosing 3 of them without repeat. Now, according to the formula, that would be 26 factorial divided by 26 minus 3 factorial. And if you do that math is going to work out to be 15,600. The other 4 entries on our license plate were numbers, and so that's a totally different permutation. We have 10 different digits that we could choose, and we were going to choose 4 without repeat. With repeat, this formula doesn't work, but we're not repeating, and so we take 10 factorial and divide it by 10 minus 4 factorial. And if you do that math, that works out to be 5,040. Now, just like we did with the number of events and the counting principle, the number of ways one thing can happen and the number of ways another thing can happen, well, the number of ways we can make our letters happen is this P26 choose 3, and then the number of ways that our letters could happen would be this permutation of 10 choose 4, and if we multiply those two numbers together, 15,600 times 5,040, we get the number that we got yesterday, or on the last video, 78,624,000. And so 2 different ways to tackle this Gotham City license plate problem. So this leads us to our next thing, which is distinguishable permutations. So in this case, we didn't have anything that was repeated, right? We had 26 different letters. We had 10 different digits. It's not like we have 26 letters and some of the letters repeat. A is different than a B, is different than a C, etc., etc. Numbers aren't repeating either. 0 is different than a 1, different than a 2, different than a 3. But what if we have a problem that looks like this? How many unique ways can the letters in banana be written? In this case, we might look at it and go, there are 6 different letters, B-A-N-A-N-A, and so that's just 6 factorial, which is not correct. That would be 720 combinations, 6 times 5 times 4 times 3 times 2 times 1. That's not how many we have, because that first A is no different than that second A, which is no different than that third A. So if I were to write the letters in banana in the way they're written now, B-A-N-A-N-A, and then I decide, you know what, I'm going to trade 2 letters. I'm going to go ahead and trade this first A with this last A. Well, it's not like they're different colors. We're not going to be able to tell the difference. They're not different in any fashion. And so if I just trade those 2 letters, I still get B-A-N-A-N-A, which is not a distinguished, unique, different ordering, right? And so we have to do this just a little bit differently. We have to try and get rid of all of those repeats. The nice thing is we have a formula for that as well. That formula I'm going to post up here in a picture. And like magic, there it is. Distinguishable permutations. This is straight from your book. It's on page 621. Suppose a set of n objects has n sub 1 of one kind of object, n sub 2 of a second kind, n sub 3 of a third kind, and so on, with n equaling n plus 1 plus n sub 2 plus n sub 3, etc., etc. I know there's a lot of letters and numbers in there. The number of distinguishable permutations of the n objects is given by n factorial over n1 factorial times n2 factorial times n3 factorial, etc., etc., etc. So what does that mean? Let's break that down. So what this is saying is we have a set of n objects. This has 6 different objects, right? B-A-N-A-N-A, 6 letters, 6 positions. But there are 3 A's, so N1 would be 3. There are 2 N's, so N2 would be 2. There's only 1 B, so we could think of N3 as being 1. If there's only 1 of anything else, then there's just 1 of that item. Notice what this is saying right here. So notice it says n is equal to n1 plus n2 plus n3 plus et cetera, et cetera, et cetera. So we have 3 a's, so that would be like our n1. We have 2 n's, so that would be like our n2. And we have 1 b, that would be like our n3. And 3 plus 2 plus 1 equals 6, the total number of elements that we have. So this says that if we are trying to figure out the number of ways that we can arrange it when we have repeats, no problem. We simply take that formula and use n factorial. N is the total number of things you have. So I'm looking at rearranging 6 different letters, so 6 factorial. But that will simply give me the number of unique or ununique ways. Ununique, is that a word? I don't know. That'll give us repeats. We don't want those repeats, so we're going to divide out the repeats. So what are the repeats? Well, we have 3 a's, and so we have to get rid of those 3 a's that would be repeated, and that's by dividing out by 3 factorial according to the rule. We have 2 n's, and so we're going to multiply by 2 factorial because we need to get rid of the n repeats. There's no repeat with the letter b. We could, if we want to, go ahead and multiply by 1 factorial to take care of the b, but 1 factorial means 1. And so you're just dividing by 1, you're not changing anything. So this 1 doesn't really need to be there, but it's not wrong if it is there. So from here, we just calculate all of these things out. So 6 factorial means 6 times 5 times 4 times 3 times 2 times 1. That's 720. And then 3 factorial means 3 times 2 times 1, which is 6. 2 factorial means 2 times 1, which is 2. If you want that 1 factorial in there, go ahead, that's a 1. And you multiply all of that out. 720 divided by 12 gives us 60. So there are 60 different ways that banana could be rearranged to be completely distinguishable, unique ways to arrange them. I'm going to go ahead and do that for you right here. And poof, like magic, there they all are. That's what I spent the last 20 minutes doing. Not really, I took a photo from your book, page 621. There's all of the combinations of banana by shuffling them all. Every single one is unique. There's not one that is a repeat of another. That's all 60 of them. We got one more video to go for this section that's going to deal with combinations. So that video is coming up next. Otherwise, have yourself a great day and stay safe out there. Stay healthy.